Welcome to the next lecture. Today we will start amplitude modulation. Till now we have learned few tools. We have learned that if we want to shift a signal in its frequency domain, what should we do? And then we motivated ourselves about the need of shifting the frequency, right? One of the reasons is antenna size, the other reason is multiplexing. I will explain that in some other lecture. Today we will start formally the amplitude modulation. What we are given is we have a message signal m of t, and m of t is the message signal. Suppose it can represent any signal which we want to transmit. It can be an audio signal. Okay, so one such example is here. Suppose m of t looks like this in time domain, and let this capital M of omega be its Fourier transform. That is, it contains the frequency information. Right now, see, my x-axis here is omega, okay, angular frequency. So you should be well aware of this. So we have another form wherein we can have y-axis as frequency f. Suppose I have here m of f, right? Where omega is equal to 2 pi f. So f is the frequency in hertz and omega is the angular frequency. And Fourier transform can be written in both the ways. But in our lectures, most of the time we will be following this m of omega. We will be writing in terms of angular frequency. So it's not any different. Suppose if here the maximum this frequency is b and this frequency is minus b. So on omega axis it will be 2 pi of b and minus 2 pi of b. Okay, so this should be quite clear from the context. Now as motivated in a previous lecture, this m of t, it is usually an audio signal, it can be a video signal. Its bandwidth is low, that is, it has the frequency components of m of t are of low frequency in few kilohertz, and you know that antenna height needed will be in few hundred kilometers, 50 kilometers or so. So what is the solution? We want to shift it to some other frequency band so that wavelength is quite less, that is, frequency is high. Now suppose we have a frequency omega c, okay, which is equal to 2 pi fc. Okay, so we will see that this fc, it is quite high than the usual frequency f on which suppose you are transmitting the signals, and the frequency is f. Fc is quite high. As an example, if f is of the range of 3 kilohertz, right, then fc, it can be suppose 30 kilohertz. Okay, as an example, and we want to shift this message signal which is having this bandwidth, this frequency for a transform which I have shown on the right hand side, to higher frequency. So what should we do? We should actually carry over this operation, m of omega plus minus omega c plus m of omega plus omega c, right? I have told in the previous lecture why we are adding why we are shifting it plus and minus side, so that it will become symmetric, so that the real signal, that the corresponding time domain signal is real. Now what is its representation in time domain? You know that it is m of t cos omega ct, right? So it means to shift the frequency, you need to multiply the message signal with cos of omega ct. Okay, in other words, as I told in last lecture also, you can treat the same problem as if you are having some sinusoidal signal a cos omega ct, right? and what you are doing is you are varying this amplitude A, in proportion to the message signal m of t. Fine. What does it mean? So it means that if you put this A is equal to m of t, right, so the corresponding signal will be m of t cos omega ct, right? And I am repeating it again and again so that it's clear to you. And its Fourier transform is half m of omega minus omega c plus m of omega plus omega c. So suppose if this were the Fourier transform of of message signal, then sorry, I should show it like it gets shifted to, right, this is omega c, this is minus omega c, and what will be this point? It is omega c plus 2 pi b, and this point is omega c minus 2 pi b. What will be this point? It will be minus omega c plus 2 pi b, and what will be this point? Minus omega c minus 2 pi b. Okay, so this type of modulation where the amplitude, right, so you can clearly see that the amplitude of this signal A, it varies in proportion to m of t. Okay, so this type of modulation is called amplitude modulation. And since we have here, if you see, I will redraw this Fourier transform little bit here. It has very important information in it. So after shifting the frequency, this is the Fourier transform. So this is omega c and this is minus omega c, right? If you see, around this axis you have two bands. See, it is symmetric around this axis at omega c here and at minus omega c here. Okay, so I will mark it with red color so that it is clear to you. What I mean is that at this point, right, it is symmetric. At this red color arrow I have shown, it is symmetric, and similarly at this point at minus omega c, this is symmetric. Okay, and if you see that the frequency information contained in this side is same as the frequency information contained in this side, we call them side bands. So this is a side band, this is also a side band, and for obvious reasons it is on upper side, we call it upper side band. And we call this as lower side band. Okay, so USB upper side band, LSB lower side band. Similarly here also you have this will be the upper side band and this will be the lower side band. Okay, so because of two bands, we will see later on we can have a scheme while there is only one side band. So because of two bands, we call this type of amplitude modulation as double side band, DSB. Okay, double side band. And one more thing about the name is, if you see the double side band modulation we have done, How are we writing the equation? Okay, so we are writing the equation as m of t cos omega ct. So later you will see next lecture we have one more modulation scheme wherein the modulated signal is m of t cos omega ct plus cos omega ct. See, this cos omega ct, since it is sort of a it sort of a carries the information, right? It is carrying on its back the message signal. It's called a carrier wave. Okay, this cos omega ct is called carrier wave. So let me mark it, the moment I have introduced it. So this m of t, this cos omega ct, or even a cos omega ct, it's called carrier wave or carrier signal. Okay, for obvious reason, sort of it carries on its back, on its amplitude, it carries the information about the message. And if you see what I have written on the lower left corner, m of t cos omega ct plus a cos omega ct. So this type of modulation we will study later. In this type of modulation, you have two things available. One is m of t cos omega ct. This m of t cos omega ct, it is called a modulated wave or modulated signal. Okay, m of t is the message signal, cos omega ct is the carrier signal, and m of t cos omega ct, the signal which is shifted in frequency to higher side, wherein the amplitude is made proportional to the message signal. That's called a modulated signal, and this is called a carrier signal. So we will study this type of amplitude modulation wherein both modulated signal as well as the carrier signal is available in the signal which is transmitted. Both components are present, but the one which we have studied in this lecture, there is only one component. There is only m of t cos omega ct which we are transmitting. Okay, so there is no carrier here, so we say that the carrier is suppressed, so we call it suppressed carrier. Hence DSB-SC. Okay, double sideband suppressed carrier. And I will now sort of recap what we have done. We had a message signal m of t, right? So let me just mark it with make some annotations. Okay, so here is the message signal, any arbitrary one, and m of omega is its Fourier transform. Okay, Fourier transform. We also say that m of omega contains spectral information. We call it spectrum also. Spectrum is, any graph, any plot which contains the frequency information of a signal. That's called spectrum. Okay, and we see that if the maximum frequency in hertz is b, which is available in the signal, we will call b as bandwidth also. So in angular frequency it is 2 pi b and minus 2 pi b. Okay, and we know that message signals are at low frequencies, so we have to shift them to higher frequencies. And we know from previous lectures, from the modulation theorem, that to shift any frequency, any signal to higher frequency, we need to multiply it with cosine signal like this. When we multiply it, we get the shifted spectrum, m of omega minus omega c, m of omega plus omega c. So in other words, we can say that we have a signal called carrier signal, which is of high frequency, a cos omega ct. We vary this a, we make this a proportional to m. In fact, let's make a equal to m. Okay, it need not be equal to m. In general, a can be any constant times m of t. Okay, where k is a constant, we make the amplitude proportional to message signal. So then the information carrying signal is called carrier signal, a cos of omega ct, and information is hidden in the amplitude. And so I can, and then we have seen that the shifted signal has this spectrum. It has two sidebands, upper sideband, lower sideband, and hence it's called double sideband. Plus there is no separate carrier term in the signal. It's only m of t cos omega ct as compared to this part on the left hand side, lower left hand side, where there will be another type of modulation which we will study later, where there is a separate carrier part also available. So in this case which we have studied today, the carrier is suppressed. There is no carrier term, so we call it double sideband suppressed carrier. And how to generate it we will see next lecture, but we have a clue here. We need to basically multiply m of t, we need to multiply with cos omega ct. So now from circuit design point of view, we need multiplier operation. Okay, we need some multiplier. So we will see, you might have studied some circuits which actually multiply the two signals. So any circuit which will multiply two signals, we will apply message signal on one side and the carrier a cos omega ct on the other side. The output of the circuit will be m of t times cos omega ct. So theoretically and ideally we have generated double sideband suppressed carrier signal. In next lectures we will see in detail what are the different ways of generating double sideband signal. Yeah, okay, thank you for watching. So wait for the next lecture. Thanks.